time, we looked at linear search, scanning a dataset one item at a time. It works, but it requires brute force. Today, we need to trade that brute force for exponential speed. Looking at our map of the 50 algorithms, binary search sits right here in the searching category, positioned as the logical upgrade to linear scanning. The core concept is something you probably figured out intuitively as a kid playing guessing games. It is incredibly simple, yet it took the software industry 16 years to write a completely flawless version of it. The theory first appeared in 1946, when John Mauchly described it during the Moore School Lectures, the founding course of modern computing. But describing an idea and successfully implementing it are two very different things. Every published version throughout the 1950s had subtle mathematical flaws. It wasn't until 1962 that Herman Bottenbroek published what is widely considered the first truly correct, bug-free implementation in print. The difficulty lingered well past the early days of computing. Years later, computer scientist John Bentley assigned this exact algorithm to over 100 professional programmers at places like IBM and Bell Labs. Given ample time to write and test their code, roughly 90% of them still produced a buggy version. The problem persisted straight into the internet age. In 2006, Google's Joshua Bloch revealed that the standard Java library and Google's own internal systems had been relying on broken binary search code for decades. How does a routine meant to find a single record among millions end up breaking the code we trusted for half a century? To understand the failure, we first have to look at the mechanics. Binary search has one absolute rule: the data must already be sorted. If the list is out of order, the logic will silently return the wrong answer. If the data is sorted, you don't start at the beginning, you look at the exact middle of the list. If that isn't your target, you check whether it's higher or lower, and permanently discard the half where it cannot exist. To do this, the algorithm tracks three positions: a low index marking the start of your search area, a high index marking the end, and the midpoint between them. Every single time you check a midpoint, you instantly collapse the remaining problem set by 50%. Let's look at this diagram mapping out a search. We are looking for the number 22. In step 1, our midpoint lands on 55. Since 22 is smaller, we drop the entire right half of the array. In step 2, the search area narrows. The new midpoint is calculated, landing on 12. Our target is larger than 12, so the left half is discarded. By step 3, we calculate the midpoint of our remaining slice, and we land exactly on our target, 22. This chart illustrates why that halving process is so mathematically powerful. Because the dataset collapses exponentially, finding one specific item out of a million sorted records takes at most 20 probes. Compare that to a linear search, which could take a million steps. If you double your dataset to 2 million records, binary search only requires one additional probe. Even searching a billion records takes just 30 steps. In theory, it is elegant. The time complexity averages at O of log n, and space complexity is O of 1, since it only needs a few index variables. But translating this math into actual code is where the disaster happens. Looking at this technical breakdown of the 60-year bug, the problem originates from a single intuitive line of code. To find the midpoint, programmers simply added the low and high indices together and divided the sum by 2. That works perfectly for small arrays, but as datasets grew, a flaw emerged. If your array has over a billion items, adding the high and low indices produces a sum larger than the maximum limit of a 32-bit signed integer. The math overflows, the computer wraps the value into a negative number, and the program instantly crashes. To fix it, Joshua Bloch showed that you have to calculate the gap between the high and low indices, divide that gap by 2, and add it back to the low index. This keeps the numbers safely within bounds. Modern Python handles massive, arbitrary precision integers natively, so it won't trigger this specific crash. But calculating the gap rather than the sum remains the only language-independent way to guarantee your search won't break at scale. Today, this logic lives everywhere. It powers B-tree database indexes, standard search libraries in C++, and version control tools like Git bisect, which searches through thousands of commits to pinpoint exactly when a bug was introduced. Just remember its constraints. If your data isn't sorted, it is entirely useless. And because it needs to jump directly to the midpoint, it requires arrays with random access memory. It will fail on a linked list. Binary search is a critical pillar of 50 Algorithms Every Programmer Should Know by Imran Ahmad. But what if we could improve on this? Instead of blindly cutting the data in half every time, what if the algorithm could make an educated guess about exactly where the target lives? We will tackle that next time with interpolation search.